Black holes, regarded as some of the most perplexing and extraordinary phenomena in the cosmos, persist in inspiring profound examination and captivation among both observational stargazers and theoretical physicists. These celestial structures, characterized by their tremendous gravitational intensity and complete absence of emitted light or energy, signify a threshold where traditional scientific principles cease to apply. Initially predicted by Albert Einstein in 1916 as a result of his general relativity framework, black holes remained mostly speculative until technological progress in the 20th century enabled indirect verification. A pivotal discovery occurred during the 1960s when researchers studying the Cygnus star group identified an unforeseen astronomical irregularity, a luminous blue star radiating potent X-rays. This star, orbiting an unseen companion, defied conventional interpretations until it was confirmed to be gravitationally bound to an enormous black hole later designated Cygnus X1. The acknowledgement of Cygnus X1 provided irrefutable proof of black holes' reality and initiated a groundbreaking phase in cosmic research. Situated approximately 6,000 light-years from Earth, Cygnus X1 possesses exceptional attributes. It is highly dense and produces a gravitational pull so intense that even light cannot evade its influence. This defining trait led to the adoption of the term black hole, aptly encapsulating the enigmatic essence of such astrophysical entities. Subsequent research unveiled a vast spectrum of black holes dispersed across the universe, with projections indicating that our Milky Way galaxy alone could harbor over 100 million of them. Despite their elusive nature making direct observation incredibly challenging, scientists have pinpointed several probable examples within our galactic neighborhood, ranging from stellar-mass black holes, the remnants of collapsed giant stars, to supermassive black holes residing at galactic cores. Their reach extends well beyond their immediate environment, significantly influencing galaxy development and disturbing the motion of adjacent celestial bodies. Matter that ventures too close is inevitably pulled toward the event horizon, the definitive perimeter, where it experiences severe gravitational elongation before being engulfed by the singularity at the black hole's center. This dramatic event, known as spaghettification, exemplifies the overwhelming power of a black hole's gravity. As objects near this edge, the variation in gravitational force across their length becomes so extreme that they are stretched into elongated, thread-like formations. The black hole's attraction overcomes the object's internal cohesion, ultimately dismantling and assimilating it into the singularity. Though black holes provide a natural platform to test the frontiers of physics, they remain profoundly puzzling. The quest to comprehend their intricacies endures, fueled by humanity's ambition to understand the very architecture of space-time and the operation of gravity on cosmic scales. These enigmatic formations stand as silent sentinels, urging human intellect to explore uncharted domains and broaden the boundaries of knowledge. Even with the closest verified black hole lying roughly 1,500 light-years away, speculative concerns about their possible effects persist. In 2021, astronomers achieved a historic breakthrough by capturing the first unmistakable image of a black hole, specifically the one at the core of the M87 galaxy. This accomplishment delivered essential revelations regarding black holes' inner workings and structure. The photograph disclosed that black holes consist of intricate regions, challenging the oversimplified notion of them being mere vacuums. Through meticulous assessment and visual simulation, experts identified three primary components within a black hole. The outermost is the event horizon, the critical boundary indicating the region from which nothing returns. Beyond it, gravity rules absolutely, drawing all substance inward inescapably. Deeper lies the photon sphere, the second domain, where light perpetually circles the black hole. Any photon that enters this area becomes ensnared by the black hole's gravity, incapable of escape. At the nucleus is the singularity, the innermost region where the normal rules of physics disintegrate. Scientific laws as we know them collapse, pushing inquiry into theoretical realms and conjecture. The complexity and uniqueness of black holes pose significant obstacles to full understanding. While many follow the general three-layer arrangement, each exhibits distinct attributes and behaviors, resisting straightforward classification. Consequently, conventional investigative strategies often fall short, necessitating innovative approaches. Since direct entry is not feasible, any probe would be instantly destroyed by the harsh environment. Indirect observation remains the central method of study. Nevertheless, researchers persist with steadfast resolve in unraveling the truths surrounding these vast cosmic constructs. Numerous hypotheses, from stellar detonations to large-scale universal interactions, have proposed plausible explanations for the formation and operation of black holes. One prominent example involved exploration of M87's center, which strongly indicated the presence of a supermassive black hole manipulating immense expanses of space. Yet the pursuit of complete comprehension advances with constant dedication, driven by the human passion for discovery and truth. Although black holes may continue to elude full clarification, unwavering scientific exploration carries the potential to illuminate the darkest regions of existence and decode their deepest riddles. In 1963, physicist Roy Kerr introduced a groundbreaking model involving rotating black holes, transforming earlier scientific beliefs. A key element of Kerr's concept is the ergosphere, a region surrounding a spinning black hole where opposing forces temporarily halt further collapse. This rare domain exhibited anomalous activity incompatible with classical physics, suggesting more profound enigmas hidden within black holes. One of the most intriguing implications of Kerr's theory was the Einstein-Rosen bridge, or wormhole, a speculative tunnel through space-time connecting distant parts of the universe or even parallel dimensions. This idea stems from the interwoven structure of reality as outlined by Einstein's relativity, wherein massive objects distort space-time and influence the movement of matter. Wormholes could serve as hypothetical shortcuts across the cosmic fabric, potentially enabling rapid travel between remote regions. Still, uncertainty surrounds their stability and usability. Though wormholes spark visions of faster-than-light voyages and time travel, significant barriers such as quantum fluctuations and intense radiation cast doubt on their feasibility. Furthermore, Einstein's equations enforce strict limits on the speed of travel through space-time. Even if wormholes could be stabilized, they might not permit velocities beyond that of light, a concept often romanticized in science fiction. Nevertheless, the wormhole persists as a metaphor for scientific imagination and innovation. Bearing the names of their conceptual pioneers, they evoke visions of alternate realms and otherworldly gateways, encouraging contemplation of realities, deeper layers, and mysteries yet uncovered. The effort to devise a unified theory combining gravity with quantum mechanics has led to continuous initiatives aimed at establishing a theory of everything, a singular model encompassing all known matter and forces. Speculation, experimentation, and theoretical dialogue continue to propel this ambition forward. At the forefront is a group of scientists whose pioneering contributions have significantly advanced superstring theory, a revolutionary departure from classical thinking. This theory proposes that elementary particles are not zero-dimensional dots, but rather minuscule vibrating filaments. Much like the strings on musical instruments, these one-dimensional threads oscillate at distinct frequencies, giving rise to the various particles and forces observed in nature. Within this conceptual framework, the universe becomes a grand orchestration, with each particle emerging from a particular vibrational resonance of fundamental strings. A compelling feature of superstring theory is its ability to account for bizarre cosmic entities like black holes, wormholes, and other phenomena forecasted by Einstein's models. As these strings traverse space-time, their motion can distort and reconfigure the very makeup of space itself. Yet, despite its intellectual grace, superstring theory is notoriously intricate, especially because it requires more than the 4 dimensions familiar to human experience. These extra dimensions, imperceptible to our senses, can be better understood through analogies, such as fish navigating a 2-dimensional pond, oblivious to the concept of height. These hidden dimensions, coiled tightly like ancient scrolls, evade direct detection, yet subtly influence the universe's formation. Although still incompletely grasped, they may clarify how the cosmos evolved and how matter spread across it. Furthermore, superstring theory has reinvigorated theoretical physics, unveiling deep relationships between complex mathematics and observable phenomena. The search for a unified framework has fostered cooperation across scientific arenas, illustrating the deep-rooted bond between mathematics and experimental science. Still, despite its theoretical allure, superstring theory lacks definitive empirical backing. Its reliance on unobservable dimensions presents notable hurdles, currently restricting its application to abstract research. Nonetheless, its transformative vision continues to motivate physicists and thinkers, leading humankind on an exceptional voyage of conceptual exploration. As we journey deeper into the realm of theoretical physics, guided by the hopeful potential of string theory, we inch closer to deciphering the universe's greatest enigmas. Standing at the threshold of a new scientific epoch, solving the puzzles of quantum black holes has long been one of the most formidable challenges for scholars in search of nature's ultimate truths. Despite innumerable efforts, a conclusive solution remains elusive, prompting Edward Witten of Princeton's Institute for Advanced Study to remark that superstring theory is 21st century physics that accidentally arrived in the 20th century. Even so, recent breakthroughs have reignited enthusiasm. Independent research groups have achieved promising outcomes, hinting that string theory might provide a full explanation within a simplified two-dimensional model as opposed to the conventional 10-dimensional version. While this signifies a promising advancement, the journey toward full comprehension is still long and intricate. The mission to craft a grand unifying theory drives exploration to the outermost boundaries of understanding, where the division between material existence and abstract theory begins to fade and the universe's most veiled truths await discovery. Probing black holes offers tremendous insight into our understanding of the cosmos. It transforms foundational assumptions and investigates the real essence of reality. The interaction between black holes and other cosmic players, such as neutron stars and gamma bursts, illuminates the complex and deeply intertwined mechanisms that sculpt the universe.